we can go ahead and get started. Today's topic is streamlining the AI data pipeline. This is our monthly office hours series. Thank you again for everyone for joining. And I'd like to welcome my colleague, Colleen Tartow, to the stage. Welcome, Colleen.
Hey, Boone. Thanks. Thanks for having me. I'm really excited. I'm also going to be joined in a little bit by my colleague, Jason Russler. He's one of my favorite people here at FAST, other than you, Boone, obviously. And he's a technical director here. I'm a field CTO. And we're going to be talking today about streamlining the AI data pipeline, because I think that's one of the most important things we need to be doing these days. So let's see. Okay, so I think about data pipelines probably far too much, right? Like I clearly need a hobby, but how do we define a data pipeline, right? And I think at its very simplest, you can think of a data pipeline as data coming in, it's being produced, right? It's being produced either by a third party or first party. You've got data coming in from perhaps an ATM, a transactional system, the edge. You could have data coming in from your smart home appliances, things like that. And so you've got that data being produced, and then the data is going to get replicated because you typically don't want to touch those production systems with your data and analytics and AI and things like that. Those production systems are sacrosanct. So you replicate your data, you ingest it into some sort of system, but the real point here is to transform it. So you want to curate that data and make it make sense to your business, apply your business logic to it. And I will say this 1,000 times, and I'll keep saying it, and I'll get off my soapbox in a second, but that is 90% of the work. Like that is most of the work, is a curation of data from whatever raw data you've got into something that makes sense for your business. And then we've got some consumption layer, right? And traditionally over the last, 40, 50 years, this has been something like reporting, data analytics, BI, and you've had some data science as well. And now, of course, the darling of the past couple of years has been generative AI. So we've kind of moved in complexity. We've increased the complexity of that consumption layer. But ultimately, this is what a data pipeline has tended to look like over the last several decades. But AI is a different beast. And I kind of want to point out a few things with this slide. So first, AI is more than GPUs. A lot of people equate AI and GPUs because you need incredible processing power to do the latest modeling and training and inferencing of data. So yes, GPUs are involved, but like I said, a very large percentage of the work that you're doing in AI is still data curation. It's still the rest of that pipeline. And so that's point one. Point two is that you'll notice this looks like a cycle. It doesn't look like a line, right? It doesn't look like a pipeline. It looks like a cycle. And that's very intentional because with AI, you've got more of a feedback loop than a pipeline. You still end up with your data capture. You can see in the blue at the bottom, you've got your events and your transactions and structured and unstructured data coming in. And I'll talk more about that in just a moment. And then you've got your data preparation. You're still doing things like filtering, ETL, ELT, enriching your data, deduping the data, and then you've got your model training. So you're actually doing the hard work with the GPU of modeling and splitting your data into training data and evaluation data, doing things like checkpointing so that you can recover if a GPU goes down, et cetera. And then you've got your model serving layer where you're actually doing things like inferencing. You've got your prompts and response. This is your chat GPT interface, right? And so this is interesting though, because that response can then be fed back into the data capture layer. So you've actually got this feedback cycle, which you wouldn't necessarily have in a more traditional analytics use case. Now, like I said, I do think about pipelines a lot. And so for me, what I like to think about is how can we flatten this out, right? And so we've made an attempt here to flatten this out and sort of starting from the collection of raw data on the left, and then you're doing some sort of refinement function, and that can typically be done with a CPU. And you take that refined or curated data, and then you feed it into the model. And then you've got either a pre-trained model or you're training a model yourself, and that's where the GPUs come in, right? And that's where you're actually quantizing the model and the data and doing the fine-tuning and the retraining and all that good stuff. That typically does require a GPU. From there, then you're actually deploying it into an inferencing layer where you've got your query and response, etc. And then you're also feeding things back, right? So you've got your query and response through RAG or retrieval augmentation can be used to actually help further refine the data to make sure that like the right answers are getting through the pipeline in the right way. And then you'll notice this sort of, dotted line transaction log store down on the bottom right. This is actually really important. This is for your audit logging and your tracking. So how do you know how things were, how answers were gotten to, right? Like how do you get to those answers? That all needs to be tracked. And so that is actually a lot of data. And speaking of a lot of data, like we did put in the blue bubbles here, you can see the volumes that we're talking about. The collection of raw data, that's going to be your biggest volume of data. That is everything. That is structured data, unstructured data, semi-structured data. And it's going to be in the order of exabytes at most of our large customers. Smaller customers might have less, but you need to be prepared for things like exabytes. When you refine the data, you deduplicate it, you do things like that, you end up reducing the data volume to maybe, say, 100 petabytes. And then when you split it out into training data and evaluation data and you further reduce it, you're going to have still on the order of 10 petabytes of data. So that's still quite a lot of data. In the end, you might get down to a terabyte of data, but then keep in mind that that transaction log store is growing somewhat exponentially, and that's going to be tens of petabytes again. So these volumes that we're talking about are orders of magnitude larger than what we've been talking about in the past with BI. So something to keep in mind. So this is sort of that flattened version of that original cycle I showed you for AI. And this is more of a pipeline. Let's flatten it one more time. So this is a very simplistic view of what we're doing here. So again, you've got your source, your data production, you've got your events, your transactions, unstructured data, and model feedback coming in. Now, unstructured data is going to be things like, videos and audio and pictures and documents. And so that's data that often got ignored in the past. And that's why we're talking about exabytes now. We're going to collect all of that data. Some of it will be streaming, some of it will be bulk load. We're going to rationalize it. We're going to make sure that we understand the data. We may catalog it, and we're going to curate it. And we're going to make sure that we're filtering, transforming, all that good stuff. Then we're going to train it. We're going to serve the model, and we're going to consume it with, both downstream applications, but then also the audit and logging. So this is just an even more flattened way of looking at it. But right now, I want to double click on the data preparation step. So this middle step, I've already told you the end result here, which I think this is like 80-90% of the work. Yes, modeling is hard, like the infrastructure is all challenging, but actually applying business logic to data and making sure it's correct and can be used in the correct way in the model, it's very important. So when we think through this curation of enterprise data, you've got data coming from a lot of different places. It can be any kind of transactional database. It could be another analytical database. It could be a third party sending you data. You could subscribe to data. You could get raw data from IoT devices. You could get data from mainframes. You've got data coming in all different ways. And that data is going to come in either in a bulk fashion or in a streaming fashion. Those are, to grossly simplify, that's how data comes in. And then you've also got your real-time data, things like interactions, application data, clickstream, stuff like that. And then you have your content repositories. So actual, if you're ingesting videos, et cetera, that's all going to get loaded in. And so that's where those exabytes are coming from. And then you have to ingest them. And typically what we do is we put the data into a data lake or a data warehouse. Some of the data will end up feeding into knowledge graphs. That's another form of data that you have to think about. And then when you curate the data, you're actually going to put it, again, in a lake or a warehouse, hopefully some sort of semantic layer so that you can understand what the correct data is, what your data products are. And there's a whole data management paradigm behind this, hopefully. And then you'll also have things like vector databases that you want to think about. And again, if you look at the volumes, we're talking about going from exabytes down to petabytes here. Now, what I think about a lot is things like what part of this data is structured, right? Like what pieces of this data are actually coming through that are more traditional, right? And I think it's largely the flow from the transactional databases into the data lakes and warehouses into the curation layer. Like we've been doing that for a very long time, right? What's new is this unstructured data flow, this real-time data and the content repositories all going into AI models. And that's sort of where the GPUs come in. That's where we're feeding into knowledge graphs and vector databases, et cetera. So we need to be cognizant of which tools we can use in which cases, how a data lake and a data warehouse and a semantic layer act when you've got data that was sourced from unstructured sources. So all fun things to think about. So when you're doing this, you want to think about having the right tools in your back pocket. And so as this is a vast webinar, I do want to mention the VAST database. The VAST database is, the crux of it is both OLTP and OLAP. The way it works is data is fed into transactional rows. So we write in rows. And then that happens in scale out SCM Flash. And then we push down into hyperscale Flash in columns. So when you're writing data into the database, you're writing it in rows. And when you're reading it, you're reading it in columns. And so what that means is that we're both very efficient on write and on read. So select queries, for example, are incredibly efficient, and you end up using fewer compute resources. So this is just one way in which we want to start thinking about streamlining the AI data pipeline by using tools that have multiple purposes rather than having two separate databases for this purpose, right? And this is all possible because of our parallel, disaggregated, shared everything architecture that we have enabling everything. And it also can go out to the exabyte scale, which is obviously incredibly important here. So what you get with this is you end up with increased ROI for your basic data and analytics use cases, but then it also works for your AI use cases. So we end up with incredibly fast write performance, read performance. You also get things like vast data reduction and things that you might have had to do and worry about in more traditional databases like vacuuming or partition management or CDC. You don't have to worry about those anymore. So this is generally like the next generation of multi-purpose databases. But that all said, let's get back to the AI data pipelines. So back to this very simplified pipeline. Now I want to talk about the model training step. We talked about the curation step. Let's talk about model training. Generally, I alluded to this earlier. You're going to take that curated data that you made in the previous step, and now you're going to split it up into training data and evaluation data. And again, you're talking about petabytes of data now. And you're going to actually either take a pre-trained model or you're going to train your own model on this data, and you're going to run the modeling, right? And you're going to run the inferencing, and you're going to actually deploy this application based on these models. And so at this point, you're actually reducing the data volume quite a lot, because in the end, what you're looking at now, you're down at gigabytes of data, which is more like a BI use case. But along the way, you've been operating. I mean, the model is only as good as the data, but the more data you feed into a model, the better it will be, right? So the more data you can push in, the better. So we're still talking about petabytes of data here. So the other point I want to make here, and I haven't really mentioned this yet, but it's incredibly important, is data security. So when we talk about BI data pipelines, things like data lineage are very straightforward. There's a lot of products out there that will give you data lineage for free. And you can generally trace where the data goes and where it comes from, and you can work backwards or work forwards. That's not the case in generative AI and in these LLMs. It's very challenging to actually understand where the answer came from. And beyond that, you also need to make sure that you're understanding access control and data security at every step of the way. Because as we know, there are a lot of regulations coming out around AI. And so the easiest way to really handle that is a zero trust approach, which means that you are going for principle of least privilege and making sure that folks only have access to the things that they absolutely need access for. And all of that access is audited and tracked. And this is something that's been coming out at the federal level for all data use cases, but it's especially important in something like this. So just little caveat there that you want to make sure that everybody is focusing on also applying a layer of data security to your entire AI data pipeline. All right, so I've talked about the pipeline itself. This sort of summarizes all of the things that I think through when I think through a data pipeline. And so on the left, you've got the legacy data infrastructure. This is more of a BI use case. You might call this the modern data stack. And on the right, you've got AI, which typically I'm talking less about machine learning that we've been doing for the past 10, 20 years, and more about things like generative AI, LLMs, computer vision, et cetera. So again, when we talk about the data types, legacy data infrastructure is built for structured and semi-structured data, whereas AI is focusing on all data, including unstructured data. Now, the legacy data, the important part here is that structured data tends to be a very small fraction of the entire data volume. And in fact, we're talking about gigabytes and terabytes, whereas when you look at the entire data volume, 95% of the data is typically unstructured, depending on the industry you're in. And so this can be petabytes or even exabytes of data. And so these are incredibly different volumes to build for. And things like performance, scalability, and cost become incredibly different conversations. So something to keep in mind. The complexity about data also changes. I mean, data is very simple to understand when it fits into a tabular format, but when you've got unstructured data coming from a lot of different places, how do you know the quality of that data? And if you're inferencing based on that data, how do you know that you're correct, right? So something to think through. Also, real-time processing doesn't tend to be essential in a legacy use case. So like BI, near real-time is typically good enough, whereas AI, streamlining that pipeline is incredibly important, right? So inferencing needs to be fast and improvements need to be fast. And so this is something to think through both on the input and output sides. The value of data. Okay, this is something I could talk about probably for hours if given a microphone, not this one. But the value of BI and legacy data, it's fairly well understood. It's largely reporting, some predictions, mostly like BI visualizations, like the stakeholders have good questions and you can answer those questions with data. I think that with AI, we have just scratched the surface. We don't know what we don't even know yet. We aren't even asking the questions that AI can answer. And I think that part of that is, skipping down to the governance layer, people are afraid of AI and they're kind of like, using it to make our lives a little better. But I think there's like a big leap that can be made. And whether or not that leap is well regulated or not will be interesting. But the consumption pattern that we get from that is that we start thinking about how machines can do better, not how humans can do better. Like ChatGPT helps me do better, but like, how do we help machines do better? And so, I think there's a lot there. And I would say that, we've only scratched the surface of the value of AI so far. And then lastly, the infrastructure layer. I love a modern data stack. You can spin up a data environment in like 2 hours. It's incredible. And you can do it in the cloud. You don't need to know anything about infrastructure. You can do SaaS products, so you don't need to manage anything. It can be really elastic. Bill me monthly and we're good. AI, when you're talking about exabytes of data, like good luck trying to do that in a modern data stack, right? The cost alone is prohibitive, but the scalability, the performance, they're just not there. So advanced compute like GPUs and whatever comes next, specialized hardware, this is all going to be required. So it's something that you really need to think through. To think through this in a different way, from a scalability, it's not just about data volume, but also accommodating large models is an interesting question because the models themselves can be on the order of like 0.5 terabyte, right? Or multiple terabytes. And so you end up with these incredibly large models that can't fit in memory themselves. So you have to do distributed and parallel models. And then you have to like checkpoint and recover those and all that stuff. So there's a scalability factor that as GPUs scale and as storage scales, like how are those things going to work together? And then also, if you need to scale further, how can you do that? How can you upgrade and maintain that environment well? It's a very complex problem. So something to think about. Performance is obviously paramount. You don't want to be, this is why we love GPUs. You don't want to be sitting around waiting for your model for 3 months. You want to train it in a day instead of a year. So you need to think about that. But then also query response time and ingestion time and curation time, and all of these things are really important. Again, checkpointing and recovery is part of performance as well, because if your checkpoint and recovery processes are very slow, then even if your model processing itself is fast, if a GPU goes down, it'll slow everything else down. Cost is obviously incredibly important. I mean, you not only have your infrastructure costs, but also a lot of our clients are using hybrid architectures because the cloud isn't serving as the perfect foil for AI use cases the way it may for BI use cases. And so we're seeing a lot of repatriation into data centers. And we're also seeing folks that have data centers but want to use cloud for burst capability or for specialized use cases. So having that hybrid architecture and that hybrid capability is really important. Also, evolution of compute resources is great, but like GPUs are expensive. So thinking about things like a hybrid architecture with a GPU cloud or an AI cloud service provider might be a really interesting way forward for a lot of organizations. The consumption model, you got to think about how you're actually serving your downstream users. And then, of course, there's always organizational costs that go into all of this because hiring data scientists is not cheap. I did mention accessibility in terms of data security. There's also a lot of risk management, regulatory compliance. Like I said, that's changing every day, and it changes faster, I think, in EMEA than it does in the US even. But there's a lot to consider there. There's also business continuity, like high availability and failover that you need to think about. So disaster recovery. And then there's what I think of as the fun stuff, the fun parts of governance, which are things like data catalogs, discovery, access control. Like how are you actually what are the mechanics of building an environment where folks have access to what they need and can do the work they need to do without putting things at risk? Now, there's a lot there, and it's all very complicated. So this is going to sound like the opposite of what I've been saying this whole time, but streamlining is incredibly important. Right? Thinking about things like every time you replicate data, you're adding latency, risk, and cost. You want to replicate data as little as possible. You want data products. You want to treat your data like a product so that when you pass the curation layer, when you're looking at the consumption layer, you know that your data has been certified. It's been, productized. And so to do that, you need really well architected data organization, data management, data architecture, and streamlined data pipelines. The more complexity you have, the more cost, the more of a challenge scalability would be, the worse the performance, and then the harder it is to govern. So making sure that things are streamlined is incredibly important. So that is a lot of talking from me. So that all said, less talk, more show. So now I'm going to bring on one of my favorite colleagues, Jason Russler, who is going to show us a live demo. Boone, do you have anything to add?
Okay. Okay, thanks, Boone and Colleen. We're going to go through a quick demo here where we're going to look at how we get some common crawl data to feed into an LLM. This was sort of a whole workflow for that, where we're going to stop at tokenization and actual model training and just deal with the first stages, which are data prep. So this means getting the data, changing into a format that we can use, which in this case is from web archive files to Parquet. We're going to identify some deduped records, do some filtering and governance of the data. We'll talk about what all that means, and then dump it out to something that a tokenizer can take. We're going to start by looking at the environment. I have here a Spark cluster that has 4 nodes. I have a VAST cluster with a database that we're going to look at it here in a second. And we have common crawl data that we pulled down. So this is Common Crawl news data. There's Common Crawl main, there's the whole internet, and this one just focuses on news. So these are 1 GB files. There's about 500 and something of them per month for this year. We're going to look at the first few files out of January of 2024. We don't have all the time to go through this massive set of data, so we're just going to go through about 20 GB of it, just to show you what the data prep looks like. So let's look at a terminal here really quick. I have prepared the data. So this is what I downloaded, and then I ran a tool called Warp Parquet, which opens up the web archive files and looks at the data that's in them and makes them in the Parquet, which is a structured data format that we can actually use. So what I'm going to do here is I'm going to kick off a job. First, I'm going to kick off the job. Then I'm going to tell you about it because they take a little while to run. This one takes about 2.5 minutes. And we're going to go ahead and look at one of these files. First, we're going to inspect the Parquet. Or, guys, excuse me, I'm doing this out of order. First, we're going to look at one of the files, like I said. These are web archive files, which is text. They're free text, gzipped, and then saved and concatenated and all run together. So we have a whole bunch of metadata about the file. And then we get down into the actual text of the HTML of the downloaded web page. Most of that HTML or code that's associated with generating the page is just stuff that you don't actually see. So it's stuff that we don't actually want to train an LLM on. So somewhere in here, who can tell where, is an actual article from a text news site. I think this first one is, let's go out. I saw some mentions of Jessica Simpson, Hello Magazine. So that's the very first one for news for 2024. So that's what's in there. That's what a web archive is. The Parquet file is this. It takes all that data, and this worked Parquet script will break it down into these fields. The fields we're most interested in here is, of course, the text of the web page, which is the body. But we also have all this other information. One of the things that the script that's running over here right now, which is not a script, I should mind you, it's a actual Spark job running on this cluster. It is called PySpark preprocess ingest and normalize into VastDB. What this job does is takes all that data and uses a library called Beautiful Soup, which is a HTML parser, pulls out the body text of it, runs it through, dedupes it here in a Spark job, then takes all the deduped information and then processes all of the patterns, all the junk out of it, which is stuff that might be in the body text of the article, which will include links, tags for images, so on and so forth. More stuff that we don't want to train that's actually in the article body itself. We take all that out, and then we insert it into a vast database table. So that job is done. Took 155 seconds. And what we should be able to do is go over here to the Vast UI first. And we're going to check it. And we're going to see that we have CC schema, common crawl. And then we have a table in there. The table has 108 rows in it, and it is about 1 GB. So each row corresponds to a page. So that makes sense. And we have 1 GB of text. So we went from 20 GB to 1 GB, just stripping out all that junk. So let's do something here. I'm going to start a Spark SQL session. What this is going to allow me to do is just write SQL and look at the tables that we just created. I'm going to switch to using our schema. A schema, by the way, is an arrangement of basically folders and tables. A schema would be a path to a table. It's a collection of tables. I'm going to analyze the crawl data. Mostly that's just to get around some noise and Spark. It only takes 12 seconds, so we'll just do it so that it quits complaining about not having a statistics file for a cost-based optimizer. And let's look. We have 108 rows, 108,000 rows, which corresponds to what we see in the Vast UI. And let's look at some of this text data. Select the body from the crawl data. We're going to just look at the first 10 articles that are in the database. These are fairly randomly chosen. We see a number of languages. We see some Cyrillic here. It depends on, you could do this over and over again and get a whole new set of languages. But here we are. But the thing to note is that it is just pure, clean text. There are no tags, no nothing. All that stuff was stripped out. This is what you want to go ahead and train with. So let's go ahead and stop that. Now we're going to run a really fun script, or really run a really fun Spark job, rather. This one is filtering and language detection. This does two main things. The first one is it goes through a library of objectionable content. So this is pretty common when you're doing web crawls. You need to somehow filter out all the content that you don't really want to get a hold of. These are news sites, but those can also be pretty objectionable, depending on how you define news. But this is just a library. This is the library of words I use. You don't have to use this one. You can go search and find libraries for this all over the place. That will give you a list of keywords for figuring out objectionable content. This particular one is really aggressive, so this will be a kid-friendly LLM when it's done. So it does that, takes all those things out, blacklists them, and then removes them from the database. The second thing it does is language detection. So it will go through and use a couple of libraries in Python for detecting the language of the article, and then creating a column in the vast database and populating it with the language. Let's see if we can see that here yet. Not yet. It's creating the blacklist first. So you can see we have crawl data blocklisted. So this is moving the text of the article to another table and then blocking it. So we're going to let this job run for a little bit. Okay, now that that's done, took about 5 minutes. We have a completed set of blocklisted tables or data. Looks like we lost about 10,000 rows, which corresponds to the blocklisted number here in the script. And we have a reduced number of crawl data, but more importantly, we now have a language here, a new column that was added. So that's what this particular script does, is blocks the data and adds language. Some other things that we might do to characterize the data that aren't in this demo, or might be sentiment analysis, where we're looking for, the neutrality, of the article to get out, heavily biased articles, things with superlative language, that kind of stuff, and maybe train on something a little bit more even keeled. But there are all kinds of libraries for working with LLMs. You can choose your poison. But here we're keeping it simple. And now we have a set of tables. Let's go ahead and take a quick look at them. Well, we can do a show tables, and we can see that we have these two tables. We have our blocklisted one. We're not going to look at that. And then we have one with additional language. So the nice thing about having a language is we can select against it now. And it looks like we have 656 articles there in Bulgarian. And then we have 31,823 English articles, which is probably what we want to train against if we're doing an LLM in English. Great. So let's do our last step. This is perhaps the easiest. All the script does is takes that table, runs an SQL command. Select everything where language equals English and dumps it out to a flat text file. And there it is. So we have all the English articles here ready for tokenization. What's fun to note is that it is $70 megabytes in length. So we went from 21 gigabytes of input data and whittled it down to 70 megabytes before we were ready to train, thus sort of demonstrating the data processing that actually happens before we start training. That's going to conclude this. Maybe we'll pick up later from tokenization to actual training. But for now, we're going to go ahead and go back to Boone for some questions.
Awesome. Thank you so much. Thank you so much, Jason. Cool. Well, I see we did get a few interesting questions here in the Q&A. I'm going to go ahead and flash these up on the screen. All right. So first question from Charles. How often are GPUs going down? Is it like a 1/5 problem or a 1 in 100 problem? What do you think, Colleen?
It's probably more like 1/5. You should Google GPU failure rates. It's actually a pretty significant problem. This is why checkpointing and recovery becomes such an interesting thing that you need to be very focused on. So one thing that, I think Jason mentioned this, but we have a few people who are very much AI experts who work here at VAST. Subramanian Kartik and Simon Golan helped Jason with that demo, which, by the way, fantastic, Jason. Thank you. And, one of the things that Kartik has worked on is a checkpoint sizer, and like how much do you actually need to checkpoint? Because it turns out that you don't need to checkpoint everything because you're actually doing it in a distributed fashion. So you only need to checkpoint individual GPU clusters. You don't need to checkpoint every GPU at all times. But it's an interesting problem because GPUs do fail a lot, especially when you're running these really intense operations. So it's something you need to think through a lot. We have a few blogs, if you look at our website, about GPUs and checkpointing and recovery.
Perfect. All right, another one here for you, Colleen. Can an AI pipeline also feed a BI use case?
Yes. So, yeah, and I guess that's a good question because I didn't really talk about that too much. I sort of just compared and contrasted the two and was like, AI is more complicated and there's a lot more considerations. But that said, you don't need to stand up two different pipelines necessarily, right? A lot of our customers, what they're doing is they will have an AI pipeline that also feeds a BI pipeline. And a lot of the structured data goes into both of them. And so you end up with the pipelines, you want to streamline it, right? You don't want to repeat work. So if you're curating your data and it can be used for both the AI and BI use cases, by all means, use the same pipeline. It's just a question of what are the end state use cases and kind of working backwards from there. It's a good question.
Perfect. We got time for one more here. Next one is, do you have other demos we can see?
Yes. Well, obviously Jason's demo is the best demo. But yeah, so we have other demos. If you look at our website, I think on our YouTube page, we have a bunch of demos, but we also, at our upcoming event, Journey into the Cosmos, we're going to have a lot of different demos, including a more built out version of the one Jason is doing. We're working on it now, but it will be, like Jason said, it will include tokenization.
Perfect. Yeah, no, we also have our bi-weekly live demos. We do these on Tuesdays and Thursdays, so you can get on with someone live on a Zoom and go through some intro to VAST stuff in between now and October. We're also going to have more webinars and stuff between now and then, so you can expect to see a lot more from us in the coming months. But why don't I, for those of you that didn't get a chance to watch the little preview reel that we showed at the beginning of the webinar, why don't I play that again now?
We're proud to unveil VAST's vision.
Build beyond.
Leveraging the VAST data platform.
we recently released a new AI assessment. So if you go over to the docs, on the right side of your screen, you'll notice there's a docs section. If you go over to the docs and scroll down to the bottom, you're going to see an option to take the AI data assessment. This is a great way to kind of see a baseline of where you're at from an AI perspective. So definitely encourage you to go and do that. But yeah, we look forward to seeing you here on future webinars and seeing you at Journey to the Cosmos in October. Thanks everyone for joining. Thank you, Colleen.
Thanks.